So I want to get to the proof of this theorem. It says that a principal ideal domain is a unique factorization domain. So I'll remind you some of the definitions. If R is a commutative ring with 1, a non-zero non-unit A in R is called irreducible if whenever you write A as a product of two elements from the ring, U times V, then either U or V is a unit, meaning invertible. So there is no way to non-trivially factor A. That's what this means. And a domain R is called a UFD, or a unique factorization domain, if every non-zero non-unit in R can be written as a product of irreducible elements. And it's not the uniqueness you have to interpret properly. It's only unique up to units and up to reordering. There is, of course, if you take the ring Z, for example, that's UFD. The num 60 is an element of Z. You can write it as a product of irreducibles. Irreducibles in this context are called prime. That's one way to do it. But you can also reorder. You can also sneak in some units. Meaning if you did it in two different ways, one way versus another way, there will be the same number of things in both lists, and you could reorder the things in some way so that you match them up to units. So like you don't have 3 and 3, but you have 3 and a unit times 3, etc. That's what UFD means, that every non-zero non-unit can be written uniquely up to reordering and up to units as a product of irreducibles. And I want to use this theorem as an excuse to introduce this very important notion of noetherian rings. And this is, again, a very wide subject, and it's rather abstract, but it's also very beautiful, I think. And it's a prime example how some rather abstract notion can give you concrete things. So here's the definition. A commutative ring R with 1 always is called noetherian in honor of M in noether if given any increasing sequence of ideals I1, subset of I2, subset of I3, etc. in R, there exists natural number n such that from that point on they're all the same. In is in plus 1, is in plus 2, is ... In other words, so strictly increasing here means the ideals are getting bigger as sets. So in other words, there is no strictly increasing infinite sequence of ideals in R. This is, in a sense, some sort of a finiteness condition. In analysis, this sort of thing is called a compactness condition. And it's an abstract definition. There's no denying it. I mean, the first time you see it, takes some processing. And it's only clear in hindsight what a stroke of genius it is to pinpoint this notion, because it's not at all obvious. But it's true that noetherian rings form an extremely rich and interesting class of rings, so it contains lots of interesting examples. For example, if you take a field and n-variable polynomial ring over it, that's a noetherian ring. Any quotient of it by a finitely generated ideal is a noetherian ring. instead of a field, you can put any noetherian ring here, and then still the same would be true, etc. So there are lots and lots of examples. I mean, you have to search quite a bit to find non-noetherian examples. On the other hand, you can prove very general theorems in this rather broad and abstract context. But so what it's saying is that if you have an ideal, another bigger ideal, another bigger ideal, another bigger ideal, ad infinitum, then after a while they have to be the same all along. So it cannot keep on strictly growing forever. The only thing that we will prove about this, unfortunately, is this little lemma that a PID is noetherian. And then we'll use this noetherianness to prove our theorem that PID implies UFT. So let's prove the lemma. Let R be a PID. And let's take a chain of ideals. Be a increasing sequence of ideals in R, an infinite increasing sequence of ideals in R. Now look, you're in a PID, so every ideal, this ideal I1, has a generator. So it looks like ideal generated by some element. I2, same deal. I3, the same thing. So they all, a random sequence of ideal just looks like this, right? So you only need to consider this sort of sequences because I'm in a PID. Only thing you need to verify is that the union of all these guys. So basically, increasing union of a bunch of ideals is again an ideal. And once you show this, when the showing this is just directly checking that it's closed under addition multiplication, and then if you take anything from this thing and any element from the ring, then the product is again in this thing. So that's a direct verification. But once you check that it's an ideal, you know that this union is equal to the ideal generated by some element for some A. Because again, you're in a PID, so every ideal is principal. But then, this element A is in A, so it's in the union of all these sets. So, A is in one of these sets. Being in a union means being in one of them. For some n in n. But now what? Look, we had this sequence growing happily. And this is the union. But now this A is already in here, which means that the ideal generated by A is already a subset of this. But AN is a subset of A, which means these two guys are actually equal. This one and A. But if this is equal to this, and these guys are all sandwiched in the middle, then they are also all equal to A. This forces A in AN, so A equal to AN, so the later ones also have to be all equal to the same thing. Okay. So we'll use this next time to show that a PID is a UFT.